For the first time in the history of science, we may have actually seen dark matter. Not inferred it, not modeled it, not argued for its existence through gravitational mathematics on a chalkboard, but seen it, detected its direct fingerprint, embedded in the light of the cosmos itself. And if what researchers are now telling us is true, then everything we thought we understood about the invisible architecture of our universe has just been shaken to its foundations. This is not a rumor. This is not a fringe theory buried in an obscure academic corner. This is peer-reviewed, data-driven, telescope-confirmed science, and the implications stretch so far beyond physics that they touch the very question of what this universe fundamentally is. Because, for 90 years, dark matter has been the greatest unsolved mystery in all of cosmology. The thing that holds galaxies together. The thing that shaped the first stars, sculpted the cosmic web, and seeded the conditions that eventually led to you sitting here watching this. And yet, for all of that cosmic importance, we had never once laid eyes on it directly. Until now. So what exactly did we see? Where did we see it? And why are some of the most cautious, rigorous scientists on the planet, people who don't use words like breakthrough lightly, saying that this might be the most significant discovery in the history of modern astrophysics? In 1933, Swiss astrophysicist Fritz Zwicky noticed that galaxies within the Coma cluster were moving far too fast. So fast that the gravitational pull of all visible matter combined was nowhere near sufficient to hold them together. The cluster should have exploded apart eons ago. And yet, there it was, intact, defying every equation in the book. Zwicky concluded that something invisible, something dark, had to be supplying additional gravitational mass. He called it Dunkel Materie, dark matter. Decades later, in the 1970s, astronomer Vera Rubin discovered the same strange phenomenon at work within individual galaxies. The stars at the outer edges of spiral galaxies were orbiting far too quickly. The math demanded the presence of a vast, invisible halo of matter enveloping each galaxy like a cosmic shell, holding everything together through sheer gravitational force, without ever once emitting a single photon of light. Rubin's work transformed dark matter from a curious anomaly into a pillar of modern cosmological theory, and it has remained standing, unshaken, and frustratingly unidentified ever since. Because here is the staggering truth. Dark matter constitutes approximately 27% of the total energy content of the universe. It accounts for roughly 85% of all matter that exists. Everything you can see, every star, every planet, every galaxy, every nebula, every atom of hydrogen drifting through interstellar space, all of it combined makes up just a fraction of what is actually out there. And for 90 years we could not tell you what the rest of it was. The leading candidate has long been a class of theoretical particles known as WIMPs, weakly interacting massive particles. Predicted by an extension of the standard model of particle physics called supersymmetry, WIMPs were tantalizing because they ticked nearly every box. They don't interact with light. They interact with ordinary matter only through gravity and the weak nuclear force. They were produced in enormous quantities during the hot, dense chaos of the Big Bang, and crucially, they should, under specific conditions, be detectable. Not through a telescope pointed at visible light, but through the gamma rays produced when two WIMPs collide and annihilate each other. Because in the standard model, every particle has an antiparticle, and when they meet, they obliterate one another in a burst of pure energy, releasing radiation with a precise, calculable energy signature. A fingerprint, a calling card left behind by annihilation itself. This is the theoretical pipeline that physicists have been chasing for decades. build sensitive enough detectors, point them in the right direction, and one day the universe might just send back a signal. The problem was, it never did. Underground laboratories in South Dakota and beneath the Gran Sasso Mountains in Italy ran experiment after experiment, shielded from cosmic background noise by kilometers of solid rock, searching for the faint tremor of a WIMP brushing against an atomic nucleus. Nothing. Particle accelerators at CERN smashed protons together at energies approaching those of the early universe, hunting for supersymmetric particles in the wreckage. Nothing. Gamma-ray telescopes in low Earth orbit scanned the sky for anomalous radiation patterns. And for a very long time, nothing. But then, in late 2025, everything changed. Astrophysicist Dr. Tomonori Totani of the University of Tokyo did something remarkably methodical. He went back through 15 years of archived data from NASA's Fermi Gamma Ray Space Telescope, one of the most sensitive instruments ever constructed for detecting high-energy radiation across the cosmos. Rather than searching for new signals in real time, he combed through what had already been collected, with fresh eyes and a new analytical framework. His focus was the Milky Way itself, specifically the region extending beyond the dense, gamma-ray saturated galactic plane, where the predicted dark matter halo should reside. He systematically identified and removed every known astrophysical source of gamma-ray emission he could account for: pulsars, supernova remnants, the violent accretion processes around black holes, stripping the data layer by layer, like peeling back the skin of the cosmos to expose what lay beneath. What remained stopped him cold. A diffuse, structured glow of gamma rays, not concentrated along the galactic plane where stars and gas and black holes live, but distributed across the sky in precisely the spherical, extended geometry that dark matter models have predicted for the Milky Way's halo for decades. The shape was not random. It was not noise. It was not an instrumental artifact. It matched, with haunting precision, the morphology of the dark matter distribution that theorists had drawn up long before this data was ever collected. And the energy of those gamma rays? Peaking at approximately 20 giga-electron volts, sitting squarely within the energy range expected from the annihilation of WIMPs with masses in the range of tens to hundreds of times that of a proton. Consistent with Einstein's own equation, E equals mc squared, playing out at the most fundamental level imaginable. Mass converted entirely into energy. Annihilation, a signal from the dark. Let that sink in for a moment. For the first time in history, a telescope has returned a signal that matches, in both spatial structure and energy spectrum, what the annihilation of dark matter particles should look like. Both criteria satisfied simultaneously. Not one, both, and the scientific community, measured, rigorous, deeply skeptical by professional obligation, is struggling to explain it any other way. Professor Carlos Frank, one of the architects of the cold dark matter paradigm, and one of the most respected voices in cosmological research alive today, has spoken publicly about the weight of this moment. He has compared the discovery of dark matter's true identity and significance to Charles Darwin's theory of evolution, a shift so profound in our understanding of the natural world that it redefines the context of everything else we know. You do not make that comparison casually. You do not make it unless the ground beneath you genuinely feels as though it is moving. And yet, science demands rigor above all else. And there are threads that still need pulling before the case can be truly closed. The first is the question of density. The strength of the gamma-ray signal detected by Dr. Totani implies a concentration of WIMPs in the galactic halo that is, by some estimates, higher than current models of particle production in the early universe would comfortably predict. The cosmic microwave background, the afterglow of the Big Bang itself, gives us a precise census of the particle content of the early universe. And the numbers, when extrapolated forward to today, suggest that the WIMP population needed to produce a signal this strong may be in tension with those early universe constraints. It's not a fatal flaw. Models can be refined. Parameters can be adjusted as new data comes in. But it is an open question, and science does not close open questions prematurely. The second challenge is the need for independent confirmation. In astrophysics, a single signal, however compelling, is a lead, not a verdict. If WIMP annihilation is truly responsible for this gamma-ray excess, the same signal should appear in other dark, matter-rich environments. The dwarf spheroidal galaxies orbiting the Milky Way, Sculptor, Draco, Ursa Minor, are among the most dark, matter-dominated objects in the known universe. They burn very dim in terms of conventional stellar light, but if WIMPs are annihilating within them, those little galaxies should be quietly glowing in gamma rays. Detecting that glow at the right energy, with the right spatial distribution, would be the second brick in what could become an unassailable wall of evidence. That is precisely where the next wave of investigation is focused. The Vera Rubin Observatory, now operational at its home in the high-altitude Atacama Desert of Chile, is surveying the southern sky with unprecedented breadth and depth, imaging the entire accessible sky every few nights and accumulating a dataset that, over its 10-year mission, will exceed 60 petabytes, 60 million gigabytes of the universe's best-kept secrets. Among its primary scientific targets are the satellite galaxies of the Milky Way, those faint, dark, matter-rich companions whose behavior has long whispered of an invisible gravitational architect. If Rubin's survey uncovers the population statistics of these dwarf galaxies in enough detail, it will powerfully constrain the distribution of dark matter on small cosmic scales, and either reinforce or challenge the picture Totani's work has begun to paint. Meanwhile, the next generation of gamma-ray instruments is waiting in the wings. The Cherenkov Telescope Array Observatory, a network of telescopes spread across sites in Chile and the Canary Islands, will, once fully operational, offer sensitivity to gamma rays at an order of magnitude beyond anything currently available. It will be capable of resolving the energy spectrum of diffuse gamma-ray signals with extraordinary precision, potentially resolving the question of WIMP mass and annihilation cross-section in enough detail to either confirm or definitively rule out the dark matter interpretation of Totani's signal. And at the particle physics frontier, the push continues. The high-luminosity upgrade of the Large Hadron Collider at CERN, scheduled to come fully online in the late 2020s, will probe energy regimes and interaction rates beyond anything previously achieved in a laboratory setting. If supersymmetric particles exist, and if WIMPs are among them, the upgraded LHC may catch one being born in the wreckage of a proton-proton collision, a direct creation, in the controlled environment of human engineering, of the same particle that may be silently winking at us from the halo of our own galaxy right now. The convergence of all of this, telescope data, particle physics, theoretical modeling, the legacy of Zwicky, of Rubin, of decades of frustrated searching, is arriving at a single electric point in time, a moment that scientists have theorized about, argued over, and quietly dreamed of for the better part of a century. Because dark matter is not merely an interesting academic puzzle, it is the scaffolding of reality itself. Without it, the first hydrogen clouds in the early universe would never have collapsed under gravity fast enough to ignite the first stars. Without it, those stars would never have clustered into galaxies. Without it, galaxies would never have merged and grown into the great cosmic web of filaments and voids that spans the observable universe today. Without dark matter, there are no heavy elements forged in stellar cores. There are no solar systems. There are no rocky planets. There is no biology. There is no you. Dark matter is not a background character in the story of the cosmos. It is the story. It is the author. And we may have just heard it speak for the first time. There will be those who urge patience, and rightly so. Science earns its credibility precisely by resisting the intoxicating pull of premature conclusion. But there will also come a day, perhaps sooner than any of us dared to believe even 5 years ago, when every thread of evidence converges, when the gamma-ray halo matches, when the dwarf galaxies confirm, when the accelerator catches the particle mid-flight. And on that day, humanity will have crossed a threshold that no generation before us has ever crossed. We will have looked into the darkness that has always surrounded us, and finally understood what was there. We will have solved the universe's longest cold case. We will have named the invisible hand that built the cosmos. And so I want to leave you with this. Right now, tonight, as you read or hear these words, the Milky Way's dark matter halo is wrapping around you, passing through you, permeating the very atoms of your body without leaving a trace. You have been swimming in it your entire life, as has every human being who has ever lived, as has every creature on this planet since life first flickered into existence. It has always been here, holding everything together, shaping everything we are, and for 90 years it looked back at us from the dark without ever blinking. But now we are beginning to blink back. So tell me, what does it mean to you to live at the exact moment in history when the universe finally begins to give up its deepest secret? Leave your thoughts below. Share this with someone who needs to feel the awe of this moment. Because we are not just watching science happen. We are watching the boundary of human knowledge move. And that is the greatest thing our species has ever learned to do.